Hello everyone, here at NAL, we have been developing a type of linear fusion reactor for the future of energy research. A preliminary question for you, the viewer, to think about is, what is the reason for using nuclear fusion? To answer that, currently energy is an important part of the economy, powering everything from the factories that build cars to the device you're watching this on. The only issue is that we've been using non-renewable fuel, which will eventually lead to a shortage due to there only being so much of it on Earth. On top of that, burning fossil fuels creates greenhouse gases, which have been hurting the environment for quite some time now. Currently, to combat this, we use renewable energy sources, like wind and solar energy. The latter half works on fusion, but instead of fusion in a reactor, it's fusion in the sun. But those have their own downsides, especially solar panels, as they can create harmful chemicals when they are created. The most common fusion reactor that we use is a tokamak, created in 1958, which sustains the fusion reaction using supercooled magnets which compress the hydrogen gas until it fuses. The concept behind fusion energy is that two smaller atoms are fused together into a larger atom through a process called fusion. Fusion reactions can output a lot of energy and is therefore a great way of producing cheap electricity. The only issue with fusion is that it takes energy to jumpstart the reaction. Atoms tend to want to stay together, so forcing two atoms to fuse together uses energy to break those bonds and combine into one atom. With fusion reactors, the energy comes from some form of compression, using magnets or lasers, all of which use large amounts of energy, which is what this project is trying to solve. With that out of the way, this has been an ongoing process here at NAL. Starting back in around 2018, the project started as a Farnsworth fusion reactor and has changed to the current model. The original one most likely wouldn't have been able to hold a vacuum, and with it using clear PVC tubing, it wasn't very heat resistant when it needed to be. The next two iterations are very similar and went through their own design processes. The first one of the two started as two acrylic tubes sandwiched between two steel plates with a rubber gasket in between. It had the issue of the acrylic being chipped from the cutting method and therefore couldn't hold a vacuum. Then, instead of using steel plates, it used two laser-cut acrylic discs to hold it together, but it ended up not meeting its expectations, so it was scrapped. The second out of the two was made by laser cutting multiple layers and sandwiching them together with acrylic. All of these had one glaring issue: power production. The original ones used solar panels to absorb energy, which ended up being inefficient and had its own problems with powering a battery. This has been a long process for NAL, but it has paid off. A lot has been learned about the materials needed to make such a project, and it's only a matter of time before this final design is ready to fire. The linear fusion reactor design is based on two concepts: the Wakefield Particle Accelerator and direct energy conversion. The idea is that two accelerators pointed at each other will create a beam of hydrogen plasma that with its energy should be able to fuse the hydrogen relatively efficiently. The main body is made out of PVC and acrylic, using them to create the desired shape. The next part of the body is the two Wakefield accelerators, which are made with copper tubes, acrylic, PVC, and a small tungsten wire in addition to two lasers and laser mounts. Each of the accelerators face into the body. The last part is the direct energy converter, which uses copper wires, copper plates, acrylic, plaster of Paris, and 3D printed parts. The plaster of Paris was added in other parts that may heat up more and therefore need to protect the plastic siding. The electromagnets are made with copper wires spun around steel plates. The steel, which can be magnetized, is there to help the copper wire with producing a substantial magnetic field. That part of the design involves placing spacers in between the coils and the body. The spacers need to be non-metal to stop issues with the magnetic field shape. The electronics are still needed to be worked out, but it'll include a power control for each laser, power control for the ionizers, power control for the magnets, power control for the whole system, and an energy output from the converter. All of these will need to be as uniform as possible to have things working smoothly. The magnets, ionizers, and laser system will have to be less than the output of the energy converter. in order to produce a net positive amount of energy. With the efficiency of a majority of the system should allow for that to happen. With the laser not taking as much energy as the magnets, and should be around the same amount as the ionizer, this won't be too much of a worry since the laser system shouldn't take up too much energy. With the main system control, it'll be able to be tuned off and on in the event of a malfunction or a leakage. The extra safety precaution will be necessary to finish this project without any hiccups. Creating fuel for the reactor is a challenge on its own, but storing it is even more of a challenge. Hydrogen is known for its ability to combust, that it's capable of seeping out of almost anything. So figuring out a way to make and store hydrogen became an issue. It was eventually figured out that to produce the hydrogen, which will be a deuterium-protium mix, I needed a 1-to-1 ratio of protium to deuterium. So a nice seller on eBay had deuterium water for $40, and that was bought for this project. The rest of the water can come from anywhere. The second part of producing it was electrolysis, which can be dangerous if not done correctly. The most cost-efficient and energy-efficient electrolyte was found to be sodium hydroxide, or lye, which if spilled on skin can break down cell walls. On its own it's dangerous, but with electricity and water it has its other dangers. Although it uses a low power source, it can still be harmful to people and therefore should have care taken when working with it. The next part was storage, and that was a bit easier. Using steel fittings and Teflon tape, the canisters were put together. The Teflon tape should help when the container is first put under a vacuum and when it later has the hydrogen added in. Along with that, there's 2 side valves to prevent gas from escaping when not in use. Altogether, this should be able to safely store hydrogen for use in a reactor. A possible issue is having air added in. To counteract this, the storage bottle will be flushed out with a preliminary run of hydrogen, and then the system will be connected to the storage bottles to allow for less contamination. If anyone knows the Hindenburg disaster, hydrogen and oxygen around an energy source can be quite dangerous, so flushing out oxygen will be an important part of safety around this project. The Wakefield Accelerator is a device created to accelerate particles faster with less energy costs than the common accelerator. To get atoms up to high speeds, like the LHC, we need miles of superconducting magnets, all of which need to be powered and cooled. With a Wakefield reactor, however, accelerators can be done in a short distance for less energy than most particle accelerators. Wakefield accelerators use laser pulses to drive plasma to high speeds. The basic concept is that a laser pulse creates a rapidly oscillating electron field, creating uneven pockets of electrons and protons acting like how a magnetic field would, trapping and accelerating the particles to high speeds in under 3.3 centimeters, compared to the 64 meters of even the most powerful particle accelerators. It'd be best described as a cheap accelerator that you can get more bang for your buck. For the reactor, the design has a 2-part system, a laser plus a laser driver system, and an ionizer. The laser driver has an adjustable focus along with the ability to pulse the diode. The ionizer is a copper tube with holes in the tube facing away from the laser, and a tungsten wire loop, both of which are connected to their respective electrodes. With the ion plasma moving towards the wire loop, some of it will be picked up by the laser pulses and sent down the shaft, colliding, hopefully, fusing the hydrogen in the plasma pulses. Because the system only needs to have a slight amount of plasma, unlike in a Farnsworth reactor, it'll only need enough energy to turn the hydrogen into a plasma, which can be done more easily at the lower pressures in the chamber. The direct energy converter uses 2 parts, coils that collect electrons and a plate that collects protons, the gradient of which will move electrons through the circuit creating energy. At least that's the basic idea. This kind of energy converter should be much more efficient than solar cells and have less parts than a steam generator. Overall, it should be a more cost-effective and efficient alternative to both of those energy collecting strategies. The design I used in my project is a small device with multiple copper coils and a copper backplate, all hooked up to separate wires to get a positive and negative output. The energy flows into a power regulator, then into a battery for use in powering the system, and hopefully something else. If the system can create a net positive output, which is possible and is the goal of this project. Overall, this project has been a wild ride, and its motivation is behind one important concept. Fusion is one of the most important things we need to research in the modern era for clean and powerful energy. The majority of our world is still powered by fossil fuels, so if this project can bring us one step forward, it'll be worth all the hard work. A big thank you goes out to the family and friends who have supported this journey, and another one should go to all of my followers on Instagram and Twitter. If you'd like to show support for this project, please like, comment, and subscribe. I'll be continuing this project until it is finished and will update all of you viewers on what happens / how it goes. Something that would be a great help would be to have some mentors and followers who can help get this idea out there. This project isn't a one and done deal. It needs support from academics, the media, and scientists to make it a reality. If you have connections, please tell them. My email will be in the description along with my Twitter and Instagram. Thank you all for the love and support. NAL.